Able to see the screen? Okay. So if you are able to see the screen, I think we will slowly start with some theory, and then after some time we will uh, start doing some questions on complex analysis. So most of you must have seen the syllabus for complex analysis. Let me quickly see now once again. The syllabus for GATE says it starts with functions of a complex variable, continuity, differentiability, analytic function, harmonic, integration, Cauchy integral theorem, formula, Liveliest theorem, maximum modulus principle, Moreira theorem, zeros and singularity, power series, Taylor, Lorentz, residue application, Roche's theorem, argument principle, Schwartz Lemma, conformal mapping, and Mobius transform. That is what the GATE syllabus. And the CSIR syllabus is somewhat similar, but they do have something called transcendental function, including the trigonometry and hyperbolic functions. They do have conformal mapping and Mobius transforms. I think the same syllabus. One thing that they have not written in the GATE syllabus, but it is there, is open mapping theorem. But even for GATE, I think open mapping theorem will be useful. Anyway, that is how the syllabus goes. Basically, it is a first course in complex analysis. The syllabus looks like in the first 6-7 chapters of Conway book. If you have the Conway book, I think the first six chapters of Conway book is what is covered in the syllabus. So let us start one interesting thing about complex numbers and complex analysis, though this may not be needed for answering a CSIR question, but let us know the difference. But in case of real line, when you talk about a graph or function, when you talk about limit when x goes to x naught, then you will be able to approach that x naught in two directions, either through the negative direction or the positive direction. Only two directions are there. But in case you consider a function from complex plane to complex plane, so you talk about w equal f of z, and when you are given a point z naught, and you can approach this point in many directions. So you can approach in many ways. Y direction you can approach in many directions. So, but in real case only two direction, but in complex case there are infinitely many directions with which you can approach z naught. That makes the theory interesting. So whenever you have a real number, complex numbers with you, you can think of functions from R to R. You can talk about R to C, and you can talk about function from C to R, and then you can talk about C to C. So you can talk about a function from each one of these spaces to the other space. So you can study about 4 different kind of functions. This is what is the real analysis. So you study about function from R to R in real analysis. This is the one which we will be studying in complex. So there is two other cases which there. One is the real valued, complex valued function of a real variable. Maybe such function will take a real variable t, and f of t will be a complex number. You may get u of t plus I times g of t and so on. So when you want to talk about derivative and all that, you can easily define the derivative, because you have u as a function of single variable and g as another function of single variable. You can talk about derivative like this. You can, if you want to integrate also, you can integrate real part and integrate the imaginary part. You can do all that theory very easily. So there is no problem talking about this function from R to C. The theory will look somewhat similar to the one from R to R. But then do we study about these kind of functions? Maybe you can think of an example like f of z equal to mod z. This is a function that takes complex variable, but it is a real valued function. Or else you can even think of argument of z. It is also a real valued function of a complex variable. I don't see anybody studying about calculus for this kind of mappings. Why they don't study? Because if you want to define limit at say z naught, then you will be considering this one. So or or equivalently, if you want, maybe at z naught you can talk about delta z minus f of z naught by delta z you will write. And maybe the limit when you consider as z goes to z naught will be considered to be the derivative. And if you want to define derivative like this, then you can see one thing. The numerator is always real valued because if you consider a function from say C to R, that is what the function here. So if you consider a function from C to R, the numerator is always real, whereas the denominator is complex quantity. So if you are approaching delta Z to 0, you can approach through either the real axis, or you can approach through the imaginary axis, or you can approach through any other direction also. In particular, if you approach through the real axis either from the left or the right, then this will be a real quantity, numerator will be a real quantity, so the ratio will be a real quantity. Suppose you approach through the imaginary axis either upward or downward, then this will be a purely imaginary quantity, numerator is a real quantity, therefore the limit will be purely imaginary. So purely imaginary quantity will come. So if the limit exists, then the real quantity should be equal to the purely imaginary quantity. Then it should be the number 0 only. So if you have a function from C to R, and if it is differentiable, then the derivative should be 0 only. There is no other option. So the only differentiable functions are those functions which have 0 derivative. So it cannot have non-zero derivative, and therefore the theory of calculus for this kind of function is not interesting. There is no fun studying calculus for this, and that is why nobody talks about calculus for this kind of function from complex to the real. That is one thing that you should know, but then let us also talk about what is analytic function and all that. Suppose you have a function from some G to C, where G is some open set in C. So that is what we will normally do. Whenever we have a function in complex plane, we always consider a subset G which is open. I think you know what is open set and all that, so I am not going to talk about them. So if you have a function defined on an open set, that function will be said to be differentiable at a point z naught, provided f dash of z naught defined by this kind of formula exists. So if you have a derivative at every point, then the function will be differentiable in G. So differentiable at z naught means the f dash of z naught exists, where the f dash of z naught is defined by this limit z goes to z naught of f of z minus f of z naught by z minus z naught. So if the derivative exists at all points in the given domain, then the function will be called differentiable in the domain G. That is what we say. So for differentiability, we need function to be differentiable at every point. And then what do we mean by analytic? So when do we say that f is analytic at a point? At a point z equal to z naught. What should happen is, around z naught you must be able to find out a neighborhood of this point. That means we should have a neighborhood of z naught inside G. On this neighborhood, the function should be differentiable. Okay, so a function is analytic at a point z equal to z naught if f is differentiable in some neighborhood of z naught. And if G is open, what we can do is, if it is differentiable at all points, then for every point what you can do is you can find some neighborhood in which the function will be analytic. Okay, so if G is open and the function is differentiable everywhere, then what will happen? For every point z naught you can find out a neighborhood in which the function is differentiable. So automatically the function f is differentiable in G, it will be analytic in G. So the f is analytic in G is always same as analytic in G is always same as f is differentiable in G. F is differentiable in G. So if you talk about the whole domain, then there is no distinction between analyticity and differentiability. Both are one and the same concept. But when you are restricting to a single point, then what we need is for differentiability, we need differentiability only at one point, whereas for analyticity, we need differentiability in a whole lot points. Okay, so we need a differentiability in the full neighborhood of Z0. That is what the story. Okay, so let me jump into quickly deriving the Kashirimon equation. The best way to threaten people is to ask questions. When you go for interviews or any such thing, suppose I don't want to select Asha in some interview, then as soon as Asha come, I will ask some difficult questions so that she become nervous. Once I make her nervous, then she cannot answer even an easy question. Even if I ask what is your name, then she will not be able to tell. So in the exam, what you will have is you will have nervousness, you will have fear, and everything will go blank. So you may not even remember the Cauchy-Riemann equation, which are so simple. In such a situation, I think it is better that we remember what is the easy method of deriving it, okay? But not a very formal definition. If you write it in the complex analysis examination, then people will not give mark. But if you want to memorize it and then, use it in the competitive exam, then there is no problem in it. So we usually write W equal to f of Z, and then Z is always x plus iy. So what I will do is I will try to find out the derivative of this. Maybe what I will do is I will find out this one. If you want to call it as f, then I will find out what is dou f by dou x. So I want to find out the partial derivative of f. So when I come here, then I can differentiate this f with respect to this variable. That means f dash of z, df by dz. F dash is df by dz, because we have one function and then another function. So maybe you can think of this as f of g of x, g of x comma y, where g of x comma y is x plus iy. So you have function of function here. So if you want to use function of function rule, we have to differentiate the first function with respect to some variable, and that variable is g. Then we have to differentiate g with respect to x partially. So you will get f dash of z, and then if you differentiate x plus iy partially, you will get 1. Similarly, if you do the partial derivative with respect to y, then you will get f dash of z, because this is z. And then if you differentiate x plus iy partially with respect to y, then you will get I. So what you can see is f dash, you get two formula. One formula is here. The second formula is minus I times dou f by dou y equal to f dash. This is the second formula for f dash. So you can equate the two formulas. Dou f by dou x will be like what? If you write f equal to u plus iv, then dou f by dou x will be dou u by dou x plus I times dou v by dou x. This should be equal to what? So the two f dash are equal. Therefore, from these two, we are getting that dou f by dou x equal to minus I times dou f by dou y. And you must be knowing that this is also the CR equation in complex form. CR equation complex form. That is very easy to derive anyway. If you don't memorize this one earlier, now you know how to derive it easily. So minus I times dou f by dou y, that will become dou u by dou y plus I times dou v by dou y. So if you equate the real part, you will get the Cauchy-Riemann equation, namely ux equal to Vy, because this one will become minus I square, that will become 1 only. So ux equal to Vy. And then if you want Uy, that will become minus Vx. So you are getting directly the Cauchy-Riemann equation without much trouble, like what you might have done. If you want sometime, if you are interested in the Cauchy-Riemann equation in the polar form, then you can even derive complex number z as r e power I theta. Z is r e power I theta. Then what you do is you will differentiate with respect to r first, you will get f dash of r e power I theta. Then differentiate this one partially with respect to r, then you will get e power I theta. So if you differentiate partially with respect to theta, then you are getting f dash of r e power I theta. Then you are getting r e power I theta, then I will come. So from this, if you multiply this by Ri, then both sides will be equal. So you will be getting R into dou F by dou R, I times equal to dou F by dou theta. So this will be the Kashirimon equation in polar form, but in the complex way. But if you write the real part and imaginary part, then you will get the usual Kashirimon equation in the polar coordinates. Usually tricky methods are given, so you can easily remember this polar form. Then what is important is that we have given formula for f dash of z. We have given one formula here. One formula for derivative is dou f by dou x. One formula is dou f by dou x. The other formula was minus I times dou f by dou y. So if you write in terms of u and v, then it is ux plus I times vx. And then this will become what? Minus I times uy plus I times vy. Therefore, this will become what? Vy minus I times uy. And you know that ux is vy and uy is minus vx. So we have two formula for the derivative now, but we can write two more formula, but each formula is interesting in their own way. This is the formula which is involving only partial derivative with respect to x. This is the formula that involves partial derivative with respect to y. And what we can do is we can write two more formula, one formula wherein we have only the variable u, not v. Because vx can be written in terms of u. So ux minus I times uy. So this is yet another formula. This one involves only u is present, no v. And if you want, we can write another formula wherein only v exists, not u. So vy is here. Uy can be written as what? Minus vx. So then I times Vx. So you can write another formula, minus Uy is Vx. So you have yet another formula. This one involves only V, involves V only, nothing else. So we have four different formula. One involves only partial derivative with respect to x. Another one involves only partial derivative with respect to y. Another one involves u only. Another one involves v only. If suppose u is given and you are asked to find out f, then you can use this formula directly. So u is given, then ux and uy can be computed, and then you can put it here and then integrate it to get f. Similarly, if you are given v alone, then you can find out vx and vy and put it here, then f dash will come and integrate, and then you will be able to get a function. Okay, so this is the idea. We may be requiring this. And also, once your function is differentiable, then we know that it is infinitely differentiable by using the Cauchy integral formula. So once you know that, then ux will be again continuous. You can even find out second partial derivative, and similarly you can find uyy also, and it can be shown that this is 0. How you show? You just write the Cauchy-Riemann equation you have here, and then differentiate it, and then you will be getting vxy. And if you differentiate uyy minus vyx will come. If you add it, you will get vxy minus vyx will come. And these mixed partial derivatives are not in general equal. If they are continuous up to second order, so then it will be equal. So using that, we can see that this equation is satisfied. This is what you call del square u, the Laplacian. So real and imaginary part of analytic functions are harmonic. What is a harmonic function? Harmonic function, you should remember this definition. So harmonic function means del square u will be 0 plus ux, uy, uxx, uxy, yy, all these are continuous. Okay, so it is not that it is satisfying Laplace equation alone. All the partial derivatives up to order should be a continuous function. Then only we can say that the function is harmonic. maybe in the exam they may ask you even like this, a function is harmonic, Laplace equation may be satisfied, but the second partial derivative uxy may not be even continuous. Uxy may not even come in this, but it may not be continuous, then you cannot say that the mapping is harmonic. So you should know the definition, and the definition is Laplace equation is satisfied plus all the second order partial derivative up to this order 2 are all continuous function. And then, since I mentioned about the continuity, let me also talk about CR equation once again. And then you must remember this statement: a function f is differentiable at z equal to z naught if if a function is continuous, then what we can do is then ux equal to vy and uy equal to minus vx. This is what we know. What about the converse? That is what we are interested in general. So usually the people say that for the converse, what is needed is the Kashirimon equation should be satisfied, and then they may say that the partial derivatives are all supposed to be continuous, like in the harmonic case, at least first order partial derivative. That is not really needed because there is a theorem called Luhmann-Menchoff theorem. This may not be there in many books, but you can use it in the competitive exams to answer question if it requires. So if f is continuous, f equal to u plus iv is just continuous, is a continuous function. I is continuous at say z equal to z naught. This also should be satisfied at z equal to z naught only. You don't need at any other point. So f is continuous at this point, and ux equal to vy and uy equal to minus vx at z equal to z naught. Then f is differentiable at z equal to z naught. So the criteria involving Cauchy-Riemann equation is the condition for differentiability at a point. So if you want to use it for checking analyticity, then what we should do is like this: if f is supposed to be analytic, f is analytic. If you want to use the sufficient condition, we can say like this: f is analytic in omega or g, analytic in g if f is continuous there, f is continuous in g, and the Cauchy-Riemann equation ux equal to vy and uy equal to minus bx is satisfied for all z in g. This is for all z in g. So whenever you talk about analytic in g, then we need the function to be continuous in g and the Cauchy-Riemann equation to be satisfied in all of g. Okay, that is what is needed. Suppose you want that f is analytic at a point, then how do you do that? Analytic at z equal to z naught, then there must be a neighborhood u of z naught where f is continuous, and CR equation is satisfied. CR equations are satisfied in U. So the CR equation should be satisfied in U. Continuity should be there in at all point in U. So these two things are needed. So CR equation is satisfied at only one point. Continuity at one point will imply only differentiability at that point, not analyticity. For analyticity, we need all these things to be true in some neighborhood. That is what you should remember carefully. So if the Cauchy-Riemann equations are satisfied, then the function will fail to be analytic provided the f is not continuous. Okay, that is what the story. So if the function fails to be continuous in G, but Cauchy-Riemann equation is satisfied, then the function will definitely fail to be analytic. But this is bare minimum that is required. F is continuous, f is analytic means it should be continuous. This is a bare minimum requirement for a function to be analytic. So many a time the Cauchy-Riemann equation may be satisfied, but f may be discontinuous, then naturally the function is analytic. So if the function is continuous, then it can fail to be analytic only because the Kashirimon equations are not satisfied. You don't need to check about the partial derivatives of u and v. So you check the continuity of f. If you see that the function is continuous, then we can go ahead checking the Cauchy-Riemann equation, and that satisfied means analytic or differentiable depending on where you are checking it, whether you are checking at one point or in the whole domain. That is what the story. Maybe I will give you a brief idea about Mobius transform, not too much about it. I will just recall because you may be knowing already complex analysis. So you may be talking about a Mobius transform as this mapping A is at plus B, C is at plus D. So AD minus BC is non-zero is what is required, because if you compute W dash, it will be AD minus BC times something. Times something will come. So if AD minus BC is 0, then W dash will become 0. Therefore, W will become constant. Constant mappings are not that interesting. They may not be conformal. So we put this restriction because of that. Okay, that is one thing that you should know. And we know that a Mobius transform like this will map circles or straight lines. Put together, we call them as circles, correct? In the complex analysis, circle means it is going to be either a straight line or a circle like this. So any one of them will be called as a circle only. Even a straight line will be called as circles. And Mobius transform maps circles to circles. That is what people normally say. But I want to see whether the straight line will go to a real circle or not. How do I know? That is what I am going to tell briefly for a minute. Suppose you have a mapping Mobius transform like this, say z plus 1 by z plus 2. Suppose I want to let us take this circle which is centered at 1 with radius 1, something like that, and we want to know what will happen to this circle by this Mobius transform. Will it go to a circle or straight line? That is what I want to know. Okay, suppose you are given a Mobius transform like this and you are given a circle like this. I want to know what kind of image that I will be getting. So what I can do is you can actually substitute, you can find what is Z in terms of W, substitute it here and then rewrite it. You may simplify it to see what kind of equation you are getting. Either a circle or a straight line may come. So you can do that way, but that will be a very laborious thing when you are in exam hall answering a objective type question. So what you can do is you can see that this will become infinity when Z is minus 2, and minus 2 is in this circle because minus 2 plus 1 will be minus 1 modulus is 1. Therefore, minus 2 is in this circle. And when you take this point minus 2 that belongs to this circle, Z equal to minus 2 belongs to this circle. The circle is centered at 1 with radius 1. So it will be a circle passing through 2 and 0 only. So if you see that the point, okay, minus 2 is,
minus 1.
I made a mistake or what? The center is minus 1 here. The center of the circle is minus 1, radius is 1, so the circle will be this one. So minus 2 is naturally on this circle, mod z plus 1 equal to 1. So this point, when you substitute it here, then you can see that this W becomes infinity. So minus 2 is going to infinity. So on a finite circle, infinity is not going to be there. But this circle is transformed to either a straight line or a circle. In a finite circle, it will not be, infinity is not there, therefore it should be a straight line only. So the image of this circle is going to be a straight line only. That you can tell easily from this, but you need to get a point on this circle, and that may probably go to infinity. If you can find out such a point, then you can use this idea to see that whether a circle really goes to a circle or something like that. Another important thing that you need to know is sometime you may be interested in finding a Mobius transform mapping one region like this. I'm quickly reviewing all this. Suppose you want to find out a Mobius transform mapping a region like this to a region like this, then anyway this is a possibility because we want this straight line to go to this circle. Then if you find the Mobius transform, then we may get the required Mobius transform, but there is a difficulty. But this may be going to the outside but not the inside portion. If you want that this portion to go to the inside of this, then what you do is you choose 3 points here. Then you can use a cross ratio to find out the Mobius transform. So you choose Z1, Z2, Z3 here. So when you choose Z1, Z2, Z3 here, then you are choosing this direction. So you are just orienting your straight line in this particular direction. It is going in this way. Z1 to Z2 to Z3, we are going in this way. So when we are going in this way, this domain is on the left side. So it is on the left side. So we want that Z1, Z2, Z3 to go to some 3 points here. Whatever point you want to choose, you can probably choose this point minus I and this point 1 and this point I you can choose. But where we want that Z1 to go, where to map Z2, where to map Z3, that you have to decide by looking at the orientation that we can assign for this 3 points. When you assign a orientation, the domain should be again on the left side. So if you assign the orientation from I to 1, 1 to minus I, then you will be coming this way. When you come this way, the domain will be on the right. But if you go this way, then your domain will be on the left side. So we want this one to be the left side. Therefore, the orientation should be like this, minus I, 1 and I. So you map this to minus I, 1 and then I. Or else you can even map to I minus I, 1 also is all right. Minus I, I minus I and then 1 also all right. Again, the same orientation is getting. Depending on your choice, you may get a slightly different mapping, but doesn't matter. But that will map the upper half plane to the interior of the circle. So this is the orientation principle. Probably you should remember this. Though I have not seen any question in the CSIR exam using this Mobius transform, but maybe in the gate they might have asked something, but let us go ahead and then let us quickly quickly tell something about some other interesting theorem. I'm not going to review everything. For example, if F is analytic in region G to the complex plane, and if it is analytic, and if G is a closed curve and so on, then integral over gamma f dz will be 0. The Cauchy theorem statement and all I am not going to tell. I am not going to worry about the Cauchy integral formula like this. Of course, there are many conditions that may be required for the curve gamma or the function f. So I am not going to review all these things, but let us only talk about one important theorem. The one which I will call open mapping theorem. I think you people know identity theorem. So maybe I will also tell about that identity theorem, because we have many problems in the CSIR that talks about identity theorem. What is this identity theorem? If you want to understand what is identity theorem, then probably you need to understand what is this Cauchy integral formula says. So if you consider the Cauchy integral formula, gamma is a closed curve, maybe a simple closed curve, and A is a point inside. So f of A is known now by a formula using this. We have a formula like this that gives you f of A. What is A? A is the point inside. F of A is the value of the point inside gamma. So for any point inside the domain, we can get the value of function. From what values? We need to know the value of function only on gamma, because f of w need to be known only on gamma. So if I know the function on gamma, so at all the points in gamma, I know the value of the function, then we can compute this integral. This integral gives you f of A. So you know the function from the values on the boundary. So from the boundary values of this domain, so we can find out the function value on any interior point. That is what the Cauchy integral formula says. That is the beauty of this Cauchy integral formula. This identity theorem is going to say something similar. It will say when a function will be identical equal to 0. This says that the function f is identically 0 if the set of zeros, if consider the set of all point z, where f of z is 0. This set z has a limit point in G. So f of z will be identically 0 in G, provided the set of zeros of the function has a limit point in G. If f is identically equal to 0, then this set z will be G, and therefore it will have limit point. That is no doubt. The converse is also true, is the identity theorem. What is the importance of this identity theorem? Because you can even prove many of the trigonometric identity in the complex case using the corresponding one from the real case. This is what we know about real numbers. So if x is real, sine 2x is 2 sine x cos x, and therefore the two functions, if you consider sine 2 is z, minus 2 sine z cos z, if you consider this as your f of z, then this function is 0 on z equal to the r. On the set of real line, set numbers, this f of z is 0 for all z in the real numbers. So real numbers has naturally limit points in C. So by identity theorem, the sine f of z is 0, therefore sine 2z will be 2 sine z cos z. So most of the trigonometric identities need not require any proof in complex analysis. They all follow from the corresponding real one by this identity theorem. That is one beautiful application. But let us not worry about it, and let us say something very interesting, and this is what open mapping theorem statement. We can understand this. Suppose you have a mapping from some open set to the complex plane, and if you consider any subset which is open, U is open, then the f of u is also open unless f is constant. So I will assume that it is not a constant. So assume that f is not a constant mapping, then what it will do is it will map any open set inside G to an open set in f of G. So f of G is somewhere here. So it will map an open set inside f of G. So you take an open set u1 u dash here, then f of u dash will be an open set here. Okay, so that way any open set will be mapped to open set by non-constant analytic function. So suppose the image is not open, then it will not be okay. So we will see an example. So for every non-constant analytic function, so we want this open set to go to open set. Let us see an example wherein the whole complex plane, the whole complex plane is going to a circle. Okay, it is going to this. The whole complex plane is mapped to this circle only. This circle only. Okay, the whole complex plane. So this is a Z plane. This is a W plane. So if you take like this, so your F is like this. So F is U plus IV. So this is a U axis, the V axis. And the whole complex plane is going to some subset of some here inside this circle. So the whole complex plane is going into this. C is open. So C is open. So by open mapping theorem, f of C should be open unless f is constant. Unless f is constant. So what we need to know is whether f of C, that means the image here, is an open set or not. This is not an open set. The whole interior, if you include, then it is open. But I am only talking about the circle. The circle portion alone I am talking about. That means what I am really assuming is that mod f is some constant. If your radius is say a or say 5 or 1, rather 1, mod f equal to 1 is what I am assuming. So if I assume mod f is 1, then this is the only portion that we are talking about, and this is not an open set. Why it is not open set? Because if you take a point here, then you cannot find a neighborhood of this point which is completely inside the circle. So anyway portion will go out, so it cannot be open. So this is not open. So f of C is not open. Once f of C is not open, then this part should be true. So f is constant. That is what you might have done. If mod f is a constant, you know that f is constant. You must be knowing this. So not only that mod f is constant implies f is constant, you can even consider any function of uv equal to 0, then u and v are the real and imaginary part of f. F is u plus iv. And you are getting some non-trivial function such that f of u comma v is 0 implies f is constant. What is this? By solving this, you can write u equal to some pi of v. That means this represents a curve in the complex plane. So that f of u comma v equal to 0 represents some curve like this. So this is what the equation f of u comma v equal to 0 means. So if your complex plane is going into some curve, then also function will become constant. This is just a special case of the open mapping theorem. Okay, so because the curves cannot be open, any curve if you take, that is not open. So even if you consider the special cases like argument of f is constant, or real part of f is constant, or imaginary part of f is constant, each one of them will represent some curve in this place. So each one of them will imply that f is constant. So that is one beautiful application of open mapping theorem. Any time you can use this. I'm interested in the Liveliest theorem because we know something called entire function. F is called an entire function if and only if f is from C to C and analytic everywhere. Analytic, okay. A function analytic from C to C is called an entire function. And you know Liveliest theorem also. What is the Liveliest theorem? Every bounded entire function is constant. This is what the Liveliest theorem. Liveliest theorem statement is this one. Liveliest theorem statement is this one. Every bounded entire function is constant. So what does it say? If you have a mapping from C to C, then bounded entire means it is analytic. That is the only thing. And bounded means it is the image is contained in a very big disk of radius. That means the image f of C will be inside this. So f of C is contained in some big disk. That means f is never become this value. F is never assuming these values. So f never become this. So whenever f is not equal to this point, say a, then I will say f omits a. If this point is b, then I will say f omits the value b. If c is here, then f assumes the value c. Okay, f assumes c, whereas f omits a comma b. That is what we will say. And essentially the Liveliest theorem says if f omits all values outside a disk, all values, because these values are not taken by our function, then our function become constant. And interestingly, there is a theorem that is more general than this Liveliest theorem that you can use. So here is the theorem called the Picard theorem. Okay, this may not be there in many syllabus, but we will just say this so that you can use it in our exam. The Picard theorem says if f is entire and omits more than one value. That means 2 points should be omitted. More than one value, then f is constant. So here f is omitting. In case of Liveliest theorem, it omits all the values outside the disk. Therefore, f clearly omits more than 2 values. So by Picard theorem, Liveliest theorem is a trivial consequence. So this Picard theorem you should remember, if f omits more than one value, then f is constant. For example, if you have an entire function from complex plane to the right half plane, so if it is going here, then naturally f should be constant only. If it is mapping the whole complex plane is going to the upper half plane, then it will be a constant only. So if you have a mapping which is entire, which maps the whole complex plane to a strip, so you consider a strip, then also it is constant. So you consider any region which is omitting more than 2 values, then that kind of mappings are all going to be constant only. Even if you consider a sector, no problem. It maps only to sector, then also constant, because it omits more than two values. It omits not just two values, more than one. So it is a generalization of the Picard Liveliest theorem. Liveliest theorem says our F omits, F maps inside the disk only. It can map to any domain which is omitting two values. Outside the domain, there are two values, then the function will become constant. That is the interesting Picard theorem. So you can use this Picard theorem in solving many questions. So I mentioned about open mapping theorem, this and that. I think other theorems, I think you may be remembering. So quickly, let me only recall the Schwartz Lemma and then start doing some problems. Okay, we are just going to recall Schwartz Lemma. Swaths Lemma. So we will just recall it. We are not recalling everything, but we will recall only this. So if you have a mapping F from say D to D closure, where D is the disk of radius 1. So you take a disk of radius 1, all these points, and that means D is the set of all Z where mod Z is less than 1. And it is mapping to the D closure. That means it can map to the boundary also. Is analytic, and f of 0 is 0. Then what we know is mod f of z is less than or equal to mod z, and mod f dash of 0 is less than or equal to 1. This is what it says. So this is the very popular Schwartz lemma, and let us see what it says before we proceed. So you are having unit disk of radius 1, and it is going to the unit disk of radius 1 again. So if you consider a disk of radius r inside, suppose you take a disk of radius r inside, then what will happen? Again you take a disk of radius r. This disk will be having image under this function f inside this only. That is what our, so this is the image of the disk. This disk will be going inside this only. It will also go inside. Why? Because if mod z is less than or equal to r, including the boundary, or if you exclude less than r, then from here what we will see is mod f z is less than or equal to mod z less than or equal to r. So mod f z also less than or equal to r. So this will map the inside portion of disk of radius r to the inside portion, somewhere inside the disk of radius r. The image is, so when the full disk is going to the full disk, any subdisk will be getting transformed into a portion of the same disk of radius r. It will be inside, it cannot go up. That is what our Swaths lemma says. And probably you might have heard about Swaths peak lemma, and where this assumption may not be there. Okay, this assumption f of 0 equal to 0 may not be there. In that case, what is the generalization of it? That is what the Swaths peak lemma. I think I will not recall it now, and then we will start looking at some problem, and then when we do the problem, wherever we need, we will recall them. Okay, this is the basic theory that you should quickly recall before you go for the exams. So let me now show you some of the questions, and probably the answer also immediately, so that we can discuss something about it. So it may be very difficult for me to scroll little bit, but the answer also may be available. That doesn't matter to us. We are not going to spend much time, and we are only going to give you the idea behind solving this kind of questions. Probably we may not even solve a question. Many questions are easy, so we will just give an idea. So you people can read the question on your own. Okay, don't wait for me to read. You can look at the first question here. F is a real valued harmonic function. That means Laplace equation is satisfied. Not only Laplace equation is satisfied, even the continuity all there for the second order partial derivatives. Probably they are interested in giving confusion to you people. That is why they wrote F instead of U or V. So you may get tempted that F is a complex valued function, but it is real valued. So it is something like uxx plus uyy is 0 is given, And using that, they have defined a complex valued function, and they have yet another function they have defined. One is the conjugate of other. One is the conjugate of the other. Here, dou f by dou x is there, and here the same thing, but with the conjugate. One is the okay, if f is analytic, then f conjugate is not analytic. For example, you must be knowing that a function is analytic if dou by dou z bar is 0. This is also a Kashirimon equation only. This is also CR equation in a very simple format. So what does this CR equation says? The f is a function independent of z bar. If z bar is there, then that function cannot be analytic, because it says dou f by dou z bar is 0, meaning there is no z bar inside f. Why this real part of f, real part of z is not analytic? Because this is z plus z bar by 2, and this has z bar in a non-trivial way, because you have dou f by dou z bar. If you compute dou f by dou z bar, then you will be getting 1 by 2, which is not 0. Cauchy-Riemann equation is not satisfied. So even imaginary part of z is not analytic because of that reason only. So a function containing z bar cannot be analytic. If f is analytic, then probably you can think of that it has a Taylor series like a naught plus a1 z plus etc. Then when you take conjugate, you will get conjugate everywhere. So that will be a function containing the conjugate. Z bar will be there everywhere. So f of z bar cannot be analytic. So only one of them will be analytic. So the option A will be wrong, correct? So you can easily rule out some of the option. I don't know why this both G and H are identically equal to 0. There is no reason to believe that this will be true. So you can. So only one of these two will be going to be the case. And we can see that either this or that will be analytic, because one is a conjugate of other. If one function is analytic, the other is not analytic. So either this or this will be naturally true. So one of them is going to be the answer. How do you decide that the B is answer? Probably you verify the Cauchy-Riemann equation for one of the function, and then you can stop there. So you have to verify only Cauchy-Riemann equation for the first function. That will anyway come from this equation. Fxx plus fyy equal to 0 will give that. G satisfy the Cauchy-Riemann equation, and therefore the answer will be B. So you can just verify Cauchy-Riemann equation. You don't need to worry about anything else, because these fx and fy are continuous, because f is harmonic. Therefore, the partial derivatives are continuous. Therefore, g will be continuous. So continuous functions satisfying Cauchy-Riemann equations are analytic. You don't need anything more than that. So you can easily identify that one of the two is answer. I'm not verifying the answer, but you just verify Cauchy-Riemann equation for G alone. You don't need to worry about H as such, because H is the conjugate of G. So only one of them can be analytic. The second question that we have here is that f is from C to C, and f of z is u plus iv, and v is given by this. So then there is something about whether it is holomorphic or something like that. I think probably you know the word holomorphic is same as analytic, and also probably it is also equivalent to regular. So all these three words are one and the same thing. Regular sometimes may mean that it may be having a removable singularity. Maybe you can talk about sin z by z as a regular function. The reason is that there is a singularity at z equal to 0 that can be removed. So such functions are called regular functions. But we will consider them as similar. Maybe for the exam purpose, you can consider them as one and the same. So here the question is to see whether f is not holomorphic or f is holomorphic or something like that. So all that will be decided by checking whether V is harmonic or not. Because if f is to be holomorphic, then u and v are supposed to be harmonic. So if you verify that V is harmonic or not, then we can decide about the question. So if you verify with the harmonic nature of this function, you can find out what is Vxx plus Vyy. you can easily see that Vx will be 3y square, therefore Vxx will be 0, and Vy will be 6xy, and therefore Vyy will be 6x. It is not equal to 0. So the function V is not harmonic. Once V is not harmonic, then V is not differentiable. Anyway, this is complex differentiable or real differentiable, that will be a good question. So if you think of complex differentiable, then this cannot happen because everything is about a complex differentiability. So assume that V is complex differentiable, this is ruled out. Then F is holomorphic on C. That is not possible because V is not harmonic. This is gone. F is holomorphic on suitable choice. This is also gone because even if you find a suitable U, then the corresponding V should be harmonic. So all these threes are gone. Therefore, this should be automatically true. If you read it, it is clear. F cannot be holomorphic on C for any choice of U. That is what the story. So this is an easy question. So this question, the next question is somewhat easy. If f is an entire function, real part of f is bounded. That means what? When you say a real part of f is bounded, real part of f, u and v, no, u is here, v is here. Real part of the function is bounded means the graph is lying between this region. So from some minus m to plus m, it is going to lie. Real part will be here. So real part lies between minus m to m means the f is going to lie somewhere between these two. So the f of z is lying in this domain. So once f of z is lying in this domain, naturally it omits so many points. So by the Picard theorem that I mentioned, f is supposed to be constant. Once f is constant, imaginary part of f is also constant. So these two are the answer. Why it is identically equal to 0? This may not be the case. Maybe you can take f to be a constant. F is what? What kind of function that you can take for showing that f is what is this? F is identically equal to 0. There is identically equal to 0 may not happen. Maybe you can take f is some constant. And if f dash is a non-zero constant, why this cannot happen? This also should
a constant and f dash is a constant. So zero.
Yeah, because f is constant, then naturally, yeah, f dash becomes 0. That is what we should conclude. So f dash is also a non-zero constant. So this f dash will be 0. Therefore, this cannot happen either. Okay, so identically 0 is not a possibility because it can be any other constant. But since f is constant by the Picard theorem, naturally f dash should be 0. Therefore, it cannot be a non-zero constant. So these two are going to be out. And therefore, A and C are possible. And the best choice of the answer, if you have to only give one answer, then it should be the C. Because if C is true, then A is automatically true. Therefore, you should choose C as the only answer in case you have to mark only one answer. If it is a multiple choice, then you can even write this one. Otherwise, you choose only the C part. Okay, before I forget, I will also tell you one kind of secret, but many of you may be knowing. And usually the team that set the paper, question paper, will be one and the same team. Every year, the same team may be setting up the question paper for CSIR, probably for GATE also. At least I know that same team is going for CSIR examination. So if you prepare topic wise, then you may get an idea of this examiner, how he is coining the question. And probably you can also identify the textbook that he is using for coining these questions. Maybe people may use the same textbook or one or two textbook, and therefore you can narrow down the textbook and then you can use that textbook for preparing for your examination. That is a possibility. So you remember that the same team may be going every time. If not entire team is same, majority of them may be the repeating people only. So majority of question may be similar, ideas may be similar from the previous year paper. Okay, that secret being revealed, let us go to this question. Here there is a bounded harmonic function in the unit is centered at origin and taking value sine 2 theta. So this question you can easily answer. Which one of them is the harmonic function is what we need. So that too, the bounded harmonic function in the unit disk, centered at the origin. So these two are not going to be bounded even. Quickly I can see that when r is 0, then this will be infinity. So this cannot be bounded. So these two are unbounded, so rule out. So which one of them is harmonic? That is what we have to choose. And if you know what is z is r e power I theta. If you write it, z square will be r square e power 2 I theta. So you will get r square cos 2 theta plus I sin 2 theta. And you can see that r square sin 2 theta is the imaginary part of z square. So w equal to z square. If you compute the imaginary part in the polar coordinate, then that is given here. So the answer should be this one only, B only. Imaginary part will be a harmonic mapping. So this is the question. You don't need to verify Laplace equation in polar coordinate to see this. That is what you have to do if you are planning to do it directly, but you don't need that. You can just identify like this. Okay, the next question is also something very easy. So you can see that you are given PQ non-zero polynomials and PQ bar is analytic. That means the Q bar cannot contain any Z bar. So then only this will be analytic. Otherwise, this cannot be analytic. So Q bar should not have any Z bar term. So if Q of Z is the polynomial, it will be something like B0 plus B1 Z plus etc. And the conjugate means the conjugate will come for everything. And if it is supposed to be independent, then what should happen? All the other coefficient should be 0. So it should be a constant polynomial. Okay, Q bar should be a constant polynomial. So that option is there. Q is constant is there. And if P is constant, it cannot be analytic then. This cannot be analytic if P is constant. You take P equal to say 1 and Q equal to say Z, and then this is not analytic. So this will not work. PQ is constant means what? PQ is constant means P is some constant by Q. RQ is C by P. Then the PQ bar will be what? P into C bar Q P bar. So P is there, P bar is there. This will contain anyway Z bar. Therefore, it's not analytic. It's not analytic. So if PQ is constant, then also the PQ bar is not analytic in general. Similar thing here, Q bar P is constant. That is exactly the function given. Then the function is analytic. If this is constant, then it is analytic. But if it is analytic, then will it imply that it is constant? That is not likely, because we have seen that as long as Q is constant, that is good enough. We don't need that whole product to be a constant. Only Q is constant is good enough. So this is the best answer. So this also looks like answer, but this is not the best answer. We are making the whole function as constant. Here we have plenty more function which are constant. Any polynomial is analytic. That is what it says. Here our class of function is restricted, only constant. So this is the best answer. This one I think I'm not going to discuss this because it will come again from the Picard theorem, because the mapping is entire and it maps to the upper half plane, and therefore you can use Picard theorem. And therefore this can be easily discussed. And here is a question that talks about the boundedness and all that of f is on to entire function, f is bounded function, f is bounded on S, g is bounded on S. So there are two functions given, and then they are talking about boundedness of f and g. So these are all probably the questions that are coming with only one option correct. So if you think of this question, then what we have to do is we have to take modulus of e power z. Probably you know that it is modulus of e power z is e power real part of z. And so if real part of z lies in this interval, namely real part of z is lying between minus pi to plus pi, our e power z also will be lying between that e power pi and e power minus pi. So it will be, mod f will be bounded. So mod f will be bounded and therefore f is bounded. So the C part is correct. So if there is only one answer to be correct, I think you have already found out which one is correct. Therefore, the other three things should be wrong. So that way you can easily do it. This question is somewhat trivial, so I will not discuss this because you are given a function from C to C where u is the real part, v is the imaginary part, and this one will come by harmonic nature of the function. This one will come harmonic nature of the function. This one says mixed partial derivatives are equal. Uxy will be uyx whenever the second order partial derivatives are all continuous. That will be the case when f is analytic. And this one is probably the wrong answer. So the first three will be true, and the question is which are true. So first three are true, the last one is not true. This one says vxy is minus vyx. Mixed derivatives are opposite in sign. This may not hold unless the function is identically zero. So this is the wrong thing. This question again, f is non-constant entire function, then which is true and all that. So if it is a non-constant entire function, then what is the first one says? Real part f is imaginary part of f. That means u and v are equal. That means the image is here. F is mapping the whole complex plane, not just this, the whole complex plane into this line. This is not an open set. So similarly, use the Picard theorem. So let us not discuss this. You can just apply Picard theorem to do this problem. Probably if you are interested, probably you can ask Steven Asen to share this file. I will share with him and he can share it with you. Again, the 10th question is also somewhat similar in nature than nature to this 9th question. So let us also omit it. The 11th question probably we can discuss. What is the 11th question says? 11th question says something about Jacobian business. The Jacobian is symmetric. That is what it says. The Jacobian is symmetric. Symmetric means A transpose is A. So if this is symmetric, then this will be equal to the transpose of it. That will be Ux and then Vx and then Uy and then Vy. So by equating the corresponding thing, Ux is Ux, nothing interesting. Uy equal to Vx is coming here. Vx is Uy, same equation. This is what we are getting. And anyway, analytic, therefore Ux is Vy and Uy is minus Vx. So by looking at these two, Uy is Vx, Uy is minus Vx, we can conclude that Vx is 0. This is at least we know. Once Vx is 0, Uy is also 0. So what we can say now is, what about f dash? That is what we have to look at it. Because once you know f dash something, we can tell something about it. What will be f dash then? F dash will be what? F dash will be something like Ux plus I time Vx. We have written 4 formula. One of the formula is this. Vx being 0, it will become Ux. So f dash is real valued. F dash is real valued analytic. Real valued analytic function. What are the real valued analytic function? That means the imaginary part of this analytic function is 0. That means f dash should be constant. If f dash is constant, f is some c is z plus d. So f is c is z plus d. Then you can see that the answer is f is a polynomial. That is anyway a polynomial only. But if is a polynomial of degree less than 1, so that is exactly the answer. So the other one is constant function, but that is not the case. It can have z also. It is a polynomial of degree greater than 1. That is not the case. It will be a polynomial of degree 1 or 0. So the answer, perfect answer is B part. And if you want multiple answer to be correct, then A is also included. But otherwise, don't select A. B is the perfect answer. If they say multiple answers are correct and you have to take all the correct answers, then A and B are all right. If f is a polynomial of degree 1 or less, then f is naturally a polynomial. You can tell that. Okay. So this is that question. Then what about this question? F is an entire function, which are correct. This one is the one which you have to use the identity theorem, correct? For this one, I think we can use for the first one, we can see the whole complex plane, because the entire function is mapping this to some straight line. Because if it is going to straight line, naturally the whole complex plane is going to be a non-open domain. Okay, because straight lines are not open. So the function should be constant. This is coming from the Picard theorem. So A is correct. And f is constant if f has countably many zeros. If there are f is having countably many zeros, the set of all z such that f of z equal to 0 has countably many zero means it is uncountable. That is what is given. This set is uncountable. Any uncountable set will have a limit point. So this will have limit point. Once it has the limit point, the identity theorem that we have, that says if the set of zeros has a limit point in C, then the function is identically equal to 0 in C. So f will become 0 in the whole complex plane. So this will also be true. So the constant itself will be 0 also. And a similar thing here by using the Picard theorem. We can say that f is constant if f is bounded on this one. So this one, I think we should find out example.
Sorry, e power
E power z, if you consider, then we know that modulus of e power z is e power real part of z. And if real part of less than or equal to 0, then the maximum will be e power 0, that is 1. So modulus is bounded, but f is not constant. So in this case, we need to remember an example. If the domain is opposite, probably we will consider e power minus z. If domain is rotated, then we will rotate it here. So sometime you have to consider e power minus z, sometime e power I z or e power minus z, depending on whether you are given real part less than or equal to 0 or greater than or equal to 0, or imaginary part of z is positive or negative. So depending on the four given domain, then you can consider these four functions. So one of them may be useful. So you just study the properties of these functions. What kind of mapping property, the e power z is a periodic function. So how this nature. So I think you should study something about the nature of this function e power z. So if f is constant, if the real part of f is bounded, I think we have seen this in an earlier question also. If we have even discussed for this earlier, a real part will be between something to something, and therefore the function will be lying in some, this one is vertical strip. So in that case, by Picard theorem, it will be constant naturally. Okay, this question is again by identity theorem. This also by by what theorem? Let us see. I will not discuss the question number 13. Looks similar. Let us see about this question number 14. F is non-constant entire function. Therefore, the E be the image. Then E is open. That is what we know by open mapping theorem. Because f is non-constant entire function, therefore f of E, f of C, which is E, is an open set. So there is again a theorem. What is the theorem that we need? If you have an entire function, if you have an entire function, then it can omit maximum one value unless it become a constant. Yeah, that Picard theorem we can use. E is open set is clear, that is clear. This empty is not a possibility because the domain will be, f of C will be maximum, either it will be C or C minus single point, C minus single point, C minus some A. Because if it omits more than 2 points, then it will be a constant by Picard theorem. So the image of the whole complex plane will be either the complex plane or complex plane minus a single point. So when you take the intersection of the image with the unit disk, you will get either the unit disk or unit disk minus a single point. So this is empty is not correct. So similarly that this is non-empty, this is all right, because many points in the real line will be there anyway, except possibly one point, so this will be non-empty. E is bounded is not correct, because E is either C or C minus A. So in both cases it is unbounded, so this is not correct. So we can tell like this. And this question is something to do with Schwartz lemma. Let us see. You are given a function which is a polynomial where the leading coefficient is 1. So this is definitely a non-zero polynomial. P is a non-zero polynomial. So you go and put a cross mark here, because P is a constant polynomial is what is given here. And this is so stupid an option, because this 1 is here. So this will be clearly a non-constant polynomial of degree n actually. So this cannot be constant polynomial. This is ruled out. But this is possible. P of z equal to z power n is possible, because every other coefficient can be 0. Then if P of z is z power n, then you can see that the Q of z is actually what they have done is they have written P of 1 by z and multiplied by z power n to get Q of z. You can just see. So you divide this by z power n, and then you will be getting this. So you have to put 1 by z and then multiply by z power n, you will be getting this. So that is the relation between Q and P. So if you do that for z power n, then you will get Q equal to 1. So that is the Q is a constant polynomial. So if this is true, naturally this will be true. So if this is true, then this is true. If Q is a constant polynomial, then naturally what is that Q? Q will be 1 only. So mod Q will be less than or equal to 1 for all z with mod z less than or equal to 1. And therefore, if this is true, then all the three things are true. So that way you can guess that all the three things will follow. But if Q is less than or equal to 1 and mod z less than or equal to 1, for mod z less than or equal to 1, then what we can see is that at origin Q is 1. At origin Q is 1. So you can even see that the function Q takes the maximum value inside. Maximum is 1 and Q of 0 is 1. So maximum is taken at the interior point. So Q is constant. What is that constant? It is 1. Once Q is 1, P is z power n. Either way, all that indicates that these three things are the answer. So you can finish it like this. But if you want to apply the Schwartz lemma, you can apply by assuming that our Q of z is z power n P of 1 by z. And you can use this hypothesis and then get that mod of Q of z is also less than or equal to 1 on mod z less than or equal to 1. So for mod z equal to 1, this will be also of modulus 1. Therefore, mod P of 1 by z will be 1, less than or equal to 1. This also will become 1. So the total modulus will be less than or equal to 1. And then Q is analytic inside the disk. It is an analytic polynomial, therefore analytic. So by the maximum principle, Q will be bounded by 1 in the entire disk. So this will come. Once this comes, I explained already that the other two also comes. So the both all the three things are answers, A, B, C. So you can discuss it in many ways. So you give whatever explanation that you feel like giving. And this one is an easy question, so I will not answer this. I wrote 4 formulas earlier, one involving partial derivative with respect to Ex, that is this, one involving U alone, one involving partial derivative with respect to Y, one involving V alone. We wrote 4 formulas, and if you take the modulus of the derivative using that 4 formula, all these things are coming. So all these 4 are answers. So this is a very easy question. So this is again, f is a non-constant analytic function, one of them is false. F is a non-constant analytic function defined on C. That means it is an entire function. So you have an entire function. So if it is an entire function, the image is the whole complex plane or the whole complex plane minus a single point. So only option is either it is C or C minus single point. So naturally then F is unbounded. This will be a correct answer. F will be automatically unbounded. Then the question is which one of them is false. So this cannot be false. This is true. So this is not an option for us. F sends open set to open set. That is the open mapping theorem. Whenever non-constant analytic function, open sets are going to open set. Therefore, this cannot be false. So it will be true. And the image of F is dense in C because the closure of C is C. C minus A also C. So this is also correct option. So all the three things are correct, and therefore this should be the only option which is false. So even without reading what is that option, we can say that that is the option. Okay, I think we will stop after one or two questions on Schwartz Lemma. Okay. So what is the Schwartz Lemma, Schwartz theorem? What is the Schwartz lemma? If you have a mapping which is from D to D closure, where is this? F is from D to D closure. Then, and if A is a point in D, then modulus of F dash of A will be bounded by 1 minus mod F of A the whole square by 1 minus mod A square. That is the Schwartz theorem. And if A is 0, then what we will get? We will get here also 0, here. So if you assume F of 0 equal to 0 as in the Schwartz lemma, then this will be 0, this will be 0, this will become totally 1. So mod F dash of 0 less than or equal to 1 will come. So that is exactly the Schwartz lemma statement. So you can say that this is a generalization of Schwartz lemma. And the second part of the Schwartz lemma was extended. The first part, mod f z less than or equal to mod z also can be extended, but that probably we are not going to use here in our questions. So let us not worry about it. So if you want to check this kind of question wherein you are given a mapping from D to D and f of 0 is given, f of half is given, which one of them is correct, you have to verify whether this formula is true or not. So you can just verify that whether these formulas are true or not, and then you can tell. So you can verify in all these cases, but anyway, the C part is both A and B are true. So if there is only one option that are needed, I think C will be the best option. Both A and B are true, you know. So otherwise, so you can verify each one of them is true. These two are true by verifying this formula. Maybe one example only I will verify. Maybe f dash of 0, mod f dash of 0, 0 here, A is 0. My f of A is then half. So it should be less than or equal to 1 minus half whole square by 1 minus 0 square. F dash of 0 less than or equal to this much. This denominator is 1, forget about it, 1 minus 1/4, so 3/4 is coming. That is what exactly we have. Similarly, you can verify that this is also true by using this formula. So both A and B are true. That is the third option, so this will be the answer. But what about this f of z equal to z? That is the question. So for that, I think we need some example to be given. So you find out an example where this is not true. Hey, do you know any example?
It is given in the question that f of 0 equal to 1 by 2. So f of
This is f of 0 is 0. Here f of 0 is 0. That
f of z cannot
possibility
be
is
equal to z.
yeah. So this is a trivial exclusion anyway. So we have 5 more minutes or how many more minutes? I think 5 more minutes.
Sir.
7, 8, 17.
Yes, sir. Yes, sir.
Then I will stop here, even though there are many other questions that we have listed out. But we have listed out questions which are somewhat easy at the later part, like residues and all that. I think directly we have to calculate. So we thought we will not discuss that, and therefore I think you people can easily handle those questions. So it is not possible to teach whole complex analysis one day. Okay, with this, I think I will stop. If you want to share any of your thoughts or if you have comments, you can share with us. Or else we will leave it to the
Particular
organizers.
questions, please ask, sir.
Don't ask me to solve a problem now, because if you have general remark or a comment, otherwise I will say some general comments.
Go ahead, sir.
So if people are not willing to ask, then we will give a general comment. You know, when I was an MSc student, I will tell the story because it will be very useful. Because I cleared the CSIR examination in the first attempt. And how I managed to clear the exam in the first attempt, because I know every theorem, every proof by heart. Because I had 30 classmates in my class, and except for the first semester, from the second semester onwards, each one of them came to my room to take a personal help. I teach every one of them. I write the theorem, I write the proof, I explain everything. So I explained every theorem 30 times. Okay. So whatever syllabus we had in our MSc, except for the first year syllabus, that I have explained 30 times to all my classmates. Even the first year syllabus, somebody who has failed, majority of them failed. I explained them anyway. So I even explained the first year syllabus, if not 30 times, I explained 20 times. So unless you practice in paper, it will be very difficult to go and write it in the exam. I used to ask this question, how many of you watch a dance program in TV? Many of us says, yes, I watch TV dance program, 3 hours of dance program I see, and 2 hours of singing, there are music shows, and then we say that, oh, the thalam is not good, surdi is not good. We say all this, but if I ask them to either dance or sing, nobody can dance or sing, unless those who went for a training. So this is the same thing.
दीदी को गलती से मिल गया था चल नहीं, ये वाला तो नहीं है, व्हाट्सएप वाला ही है। हाँ अभी मैं थी होंगी भी। चलो ठीक है, आप लोग ठीक है? हाँ चलो ठीक है।
It also makes women perfect, so it will make everybody perfect. So you go and practice. Okay, with this, thank you, Sivanesan. Thank you all for listening.
Thank you very much. Meticulous detail and very clear ideas how to approach problems. Thank you very much, sir. I think our